So let's look at one more of these Venn diagram problems where we're comparing sets. And let's say now I want to compare the sets A intersect B, union B intersects C. So this was the one from our earlier example. And the set C minus A, union B. So we drew the Venn diagram from this for this one last time. So I'll draw it here so we have it. You can go back and watch the previous video if you want to see that Venn diagram. So this would be this region here and this region here. So here, let's draw the Venn diagram. A, B, C. So I'm going to shade in C minus A first in blue. C minus A would be all of this region. And now let's shade in B. B is all of that region. So then when you take a union, you're looking for any region that was shaded at all. So my diagram would be all of this and then all of this. So it looks like the region that was shaded on the left is contained in the region that was shaded on the right. So we're going to say that A intersect B, union B intersects C. It's a subset of the set on the right, C minus A, union B. And so now we need to prove this. So let's write the outline of our proof. So you start with X as an element of the left. And then, right, this is our start. And then where do I need to end? I need to end with X being in C minus A union B. So the end, let's go down here and put the end is that X is in C minus A union B. So this means X is either in C minus A or X is in B. So that's what I'm trying to work to, and we're going to work forward now. If X is in this union, that means it's in at least one of them. So A intersect B, or X is in B intersects C. And because you have this or here, you're going to have to proceed with cases here. So case 1, X is in A intersect B. And remember what you're trying to get to. This means that X is in A and X is in B. But that was one of the two things I needed to get to. So now let's look at case 2. Case 2 is that X is not in A intersect B. Well, that means it had to have been in A intersect B or B intersect C. So this means that X is in B intersects C. That means X is in B and X is in C. So, but remember X is not in A intersect B. So X is in B, but it's not in A intersect B. So that means that X is not in A, but X is in C, and it's not in A, that tells you that X is in C minus A, which was the other thing we needed to get. So now that we've outlined the proof, you can go back and write the formal proof now, and make sure when you're writing it to reference your outline. So the proof, I would say, let X be in A intersect B union B intersect C, then X is in A intersect B, or X is in B intersect C. We proceed with cases. I'll say the cases the two cases. X is in A intersect B, and X is not in A intersect B. So case 1, assume X is in A intersect B, then X is in A, and X is in B. Case 2, assume X is not in A intersect B, but since X was in A intersect B, or X was in B intersect C, then that means that X is in B intersect C. Then we have X is in B, and it's in C. But since X was not in A intersect B, and X was in B, then X is not in A. Since X is in C, and X is not in A, X is in C minus A. So you'll say in either case, X was in B, or X was in C minus A. So that means, therefore, X is in C minus A union B, and we can conclude that A intersect B union B intersect C is a subset of C minus A union B. And there's the end of my formal proof there.